It's not rocket science. You've all heard this phrase before. This is used as a metaphor for something that sounds not so challenging or difficult. But have you ever stopped to wonder why rocket science is considered so hard and difficult in the first place? Let's find out. I'm Akshita Krishnamurthy, your friendly next-door rocket scientist and MIT PhD, bringing you out of this world space and tech content. Rocket science is often used as a metaphor for something that's mind-bendingly complex, and for a good reason. But rocket science does not just mean building rockets. It encompasses math, engineering, astrophysics, and so many more areas. It's the art and science of sending both machines and humans beyond the pull of Earth's gravity and bringing humans back to Earth safely. First, let's talk about the sheer scale of challenges involved. This is similar to planning a road trip. Imagine you're going out with your friends on a road trip. You need a car, you need a map, you need fuel, and also you need some snacks, right? Similarly, if we were planning a trip, not just across cities or states, but let's say beyond planetary boundaries, millions of miles away, and also where the environment for humans is very hostile, imagine how much more planning and preparations you would need to do. And there's not even food or water or roadside assistance to bank on. This is the kind of challenge that rocket scientists like me deal with regularly. One of the first major hurdles is actually getting off the ground. Rockets must first overcome the Earth's gravity, the force that keeps us all comfortably grounded. But if we ever wanted to leave the planet, it does not let us go so easily. And to do this, rockets have to reach what we call as the escape velocity. And for Earth, the escape velocity is actually 11 kilometers per second. Not per hour, per second. You heard it right. That converts to 40,000 kilometers per hour. Can you imagine what speeds we might have to be at to be able to escape the Earth's gravity? And if that's not enough, imagine the kind of engineering that these rockets need. Every single part must work perfectly together, and that means at speeds of 40,000 kilometers per hour, sustaining temperatures of 4,000 degrees Celsius or more, and on top of that, intense mechanical vibrations during launch. One small malfunction can mean the difference between a successful mission or a catastrophic failure. And remember, these missions cost hundreds of millions of dollars, and they take years and decades to build. Second is guidance and navigation. Space is vast and empty, and navigating it needs precise calculations. We use complex math to design what we call launch trajectories. These are the paths that the rockets take to get from the launch site to space. A series of maneuvers are used to either inject the spacecraft into a particular orbit or to set it into a trajectory towards another planet. We even exploit planetary gravity, and this technique is called gravity assist. Here's a cool animation showing how this is done. This is like a gravitational slingshot where the spacecraft gets a speed boost by flying by another planet. And this is done without requiring large amounts of fuel. So as the spacecraft gets closer to the other planet and enters its gravitational field, the planet's gravity starts pulling the spacecraft. The spacecraft passes close to the planet, optimizing the gravitational effect. And as it flies past the planet, it accelerates due to the planet's gravity. The closer the approach, the more significant is the change in speed and the direction. It can be used to accelerate, decelerate, or both, and sometimes just change direction of the spacecraft. For missions re-entering the Earth, there's also a precisely controlled angle at which the trajectories are defined. Too steep an angle and there's a lot of structural and thermal load. And while too shallow an angle might make the spacecraft slip back into space. And then we need landing maneuvers to safely land the spacecraft back on Earth. The third hurdle is communication. Spacecraft venturing outside Earth have to often communicate with us over immense distances. And these signals can take sometimes minutes or even hours to travel, especially when they're far away from us. For example, the time it takes for a signal to travel between Earth and Mars depends on its relative positions around the Sun. And this time can range between 3 minutes when Earth and Mars are closest, versus when they're farthest, it can take as long as 22 minutes. Now, the fourth hurdle is precision landing. The ability to land a spacecraft on another planet or asteroid with pinpoint accuracy is a testament to both the amazing problem-solving skills and incredible engineering of our rocket scientists. Imagine trying to drop a basketball through a hoop that is on one side of a football field all the way from the other side. That's the kind of precision it takes to be able to do a planetary landing. And the fifth and last is the human aspect. Astronauts in space deal with incredible challenges, and that includes the effects of microgravity on their physical bodies, but also the psychological stress of being isolated from everything that's familiar to them. And not just that, they also need life support systems, which includes oxygen supply, carbon dioxide removal, humidity control, temperature control, and so much more. They're also exposed to extreme amounts of radiation, and they need radiation protection as well. This is why the journey from concept to actually building and launching a spacecraft is a hard and arduous one, often taking years or even decades to complete. And this is why when something is so hard and challenging, we use this metaphor that says something is or isn't rocket science. The robots you see on Mars today were actually designed, built, tested, and then launched. But this was done over several years. And here are the coolest images from the Martian surface thanks to all of that hard work. So next time you hear somebody say it's not rocket science, you'll know just how complex and challenging rocket science is. And remember, it's not just about building rockets, it's actually being able to push the boundaries of human knowledge and capacity and overcoming the toughest challenges. If you like this video, make sure to like and subscribe.